Okay, in this section we're going to be taking a look at how to solve polynomial inequalities, and we will be considering the less than case, the less than or equal to case, the greater than case, and the greater than or equal to case. While the main method that we are going to be concentrating on will be solving these polynomial inequalities algebraically, we will also be considering the graphs in some of these problems as we look at the solutions, because it's a good way for you to visualize what is happening as you go through the mechanics of solving it algebraically. So in this very first diagram, I have provided you with a picture of a polynomial function. That function, being second degree, would be a parabola, and so here you see the parabola being graphed. You can see that the x-intercepts are 2 and 5, which serve as what's referred to as the boundary points when you are using it for purposes, when you're using the graph for purposes of solving the inequality. For instance, you could address what portions of this graph represent the solutions for the greater than case, and you can also look at what portions of this graph represent the less than case. The portion of this graph that is above the x-axis, such as this blue leg right here, there is a portion of that leg that's in blue and above the x-axis. Likewise over here, a portion in blue and it's above the x-axis. Portions of the graph that are above the x-axis, all of the x values on those portions stand for the solutions in the greater than case. So above the x-axis represents greater than. So greater than all of the solutions, those x value solutions, those will be x values that lie in the portion that's above the x-axis. That's what you're going to be looking for if you're asked to look at a diagram and find the solutions for a greater than case. If you're asked to look at a graph and to find the x values that represent the solutions for the less than case, then those will be the x values on the graph, on the portion of the graph that's below the x-axis. So the less than solutions, and you'll be asked to do this for some of the problems in My Math Lab. Just get the answer by looking at the graph. So I wanted to supply you with a picture where we can discuss that. So that'll be any of the x values that are on the graph below the x-axis. Okay, so I have put for you out here that the x values that are associated with this, the right side of this graph in blue, those are values that start at 5, and then since this leg expands further and further to the right, those would be all values greater than 5, like 6, 7, 8, 9, 10. I know this looks like it goes straight up, but it actually expands into positive infinity. So we say that part of the graphs that represent the part of the graph that represents the solutions for the greater than case would be anything from 5 to positive infinity as it flares infinitely to the right, and then any of the x values that go from negative infinity out here right up into 2, because again this leg does flare infinitely to the left. So that would be negative infinity all the way to the number 2, but not actually including those points, because at those points it actually switches behavior, and then you also see that we do not have an equal sign here. So that's why that's the main reason why we're not including we're not going to be encasing that endpoint with a bracket if we were going to give it an interval notation, but more on that to come. Then as far as the values on this graph that are less than, that represent the less than case, that would be this portion right here. And you're always giving the x values that are associated with the portion either below or the portions above. So that would be all x values between 2 and 5. Okay, moving on to the examples that we're going to be working ourselves. Most of them, as I said, are we're going to be taking an algebraic technique to find these solutions, but we will return to looking at the graph later on in this lecture. Okay, so here are the steps for solving algebraically. The first thing that you're going to want to do is factor the polynomial, because if it's a polynomial, it's going to be second degree or higher. Now, sometimes you will be able to skip the step of factoring because they've already done it for you. So this is already in factored form. Once you have it in factored form, you're going to set each factor equal to 0 in order to get the boundary points. And we're going to be doing this on a number line. Remember, we're taking an algebraic approach to getting this solution. So it's x plus 7 equal to 0 and x minus 4 equal to 0. Okay, this is going to give you, when you bring the 7 over here, x equal to negative 7. This is going to give you, when you bring the 4 over here, add 4, you're going to get x equal to 4. You're going to put these numbers on a number line and only put the numbers. You don't need to put any additional numbers like 0 or anything like that, because then you're going to think you have extra intervals. These two numbers create 3 intervals, one to the left of 7, one in between negative 7 and 4, and one to the right of 4. And you want to test each of the intervals. So the very first thing you're going to do is create your boundary points. That will create intervals, and you're going to test each of the intervals. So you're going to have to choose tester values in each interval. Try to pick the smallest ones you can and try not to pick fractions if you can help it. So I am going to choose out in this interval, I'm going to choose negative 8, so I will be testing that. In this interval right in here, whenever I can grab a 0, 0 always occurs between a negative and a positive. I like to choose 0. So I'm going to use negative 8 to represent this interval. I'm going to use 0 to represent this interval. And by testing just one number in a particular interval, it represents the whole interval. So if this one number that you're using works, everything in that interval works. And then I'm going to use 5. Okay, so these are my tester values. And then basically, as the name implies, you are going to test them in the original inequality. So you're going to use each value in the original inequality. Okay, so here we go, using the first one. I have a negative 4 in there. I have a positive 7. If the value that I'm testing, right now I'm going to be testing negative 8. If it creates a true statement, in other words, a value that's greater than 0, then that means that value works, and therefore every value in that interval works. Okay, so I'll put a yes if it works and a no if it doesn't work. And then we'll go and put the final solution in interval notation as these instructions indicate. Okay, so we have negative 12 here. We have negative 1 here. So we have positive 12 is greater than 0. That does happen to be true. Therefore, yes, all numbers in this interval work. Everything from negative infinity to negative 7. Now, because this does not have a little equal sign, we will be using parentheses when we do our interval notation. Okay, so I've tested one value. Now I'm going to test the 0 in the original inequality. So it's 0 minus 4 and 0 plus 7. Is that greater than 0? See, it starts off as a question which you are trying to answer whether it is true or false. So this is going to be negative 4. You can already see that it is going to be false. Okay, so that's negative 28. And is that greater than 0? No, that's a false statement, so that doesn't work. So that's a no. Nothing in this area works. And then let's try that last tester value, which I decided I was going to use 5. Okay, so plugging again right into this inequality, it's 5 minus 4, and then it's 5 plus 7. Is that greater than 0? Well, this is going to be 1 times 7. And yes, that's a true statement. You have 7, and 7 is definitely greater than 0. So yes, this works. When you go to give this answer in interval notation, you're going to do what you do every single time you give interval notation. You're going to read the solutions from left to right so that you are giving the smallest values first and the largest values last, which is mandatory when you're doing interval notation. You are only going to be picking up answers or stating answers for the intervals that say yes. So we're going to give that interval as part of our answer, and we're going to give this interval as part of our answer. Okay, because nothing in the middle works. All right, here we go. So this interval right here is called, everything out here is called negative infinity up to and including negative 7. So everything from negative infinity to negative 7, that's where some of the answers are. Or, see if maybe I can move this over a little bit. Try and write a little bit smaller, running out of room here. Okay, so final solutions are negative infinity all the way up to, but not including, negative 7. Again, I'm using these parentheses because there's no equal sign here. Otherwise, I would be using a bracket. Or you can also find answers anywhere in the interval from 4 to infinity. Okay, and that is your final solution in interval notation. Okay, let's move on to the next problem. And basically what I'm going over with you is the thing that messes students up in every single chapter, which is the factoring, but it's the mainstay of any algebra class. So you have to know how to factor. So going over all these factoring methods, we now have a quadratic trinomial. And so you can use the guess and check method for that, even though there are other methods that you can use, but it's easy enough and these numbers are small. So when I go to factor this, it's going to factor. We're going to break up the x squared into x times x. And then we're going to break up the back term into numbers that multiply to give you 18, but also add to give you negative 9. So that's going to have to be negative 6 and negative 3. Bring down that inequality symbol. And then you know from these factors, that's where you get your boundary, or you can also call them cut points. So, and you can just look to see what would zero this number out. That would be x equal to 6. I mean, you can create little equations out of them if you'd like, but they're easy enough to see what would zero them out. So this is going to be one of our boundary points, and this is going to be another boundary point. X equal to 3. Okay, like I say, you can call those boundary points. or you can call them cut points, because they actually cut up your number line into different intervals that you're going to be checking. Okay, so here's your number line right here. Put 3 on there, put 6 in there, then don't forget you're going to use your test points. So you need to select what you're going to use for a test point. So I'm going to use the number, let's see, what would become right before here, close as I can get to 3. I'm going to use this as a test point. And in between 3 and 6, I guess I'll use 4 as a test point. And then out here, and you can even use 0 in here if you like. That would be, it's pretty easy to use, but it's up to you. And then over here, I'm going to use 7. Okay, don't forget, these are the test points. And you're just going to start testing them in the original inequality. So I'm going to put, you can put them right in here. I mean, the danger if you put them in here is that you could have possibly factored it wrong, but I guess the whole rest of the problem is going to go wrong if you did that wrong. So here we are. We're going to test whether 2 is a solution. Remember, this 2 represents all numbers in this interval. So I'm going to go 2 squared minus 9 times 2 plus 18, and let's see whether or not this yields a true statement. It'll be true if it's less than or equal to 0. So I'm getting a 4 here, I'm getting an 18 here, and I'm getting a positive 18 right here. Okay, 2 squared is 4, 9 times 2 is 18, but with a negative, and then I had a positive 18. These 18s cancel, and I end up with the statement 4 is less than or equal to 0, which of course is false, and therefore no, none of these numbers right in here work. Okay, checking 4 now. So now I'm going to check 4, so it's 4 squared minus 9 times 4 plus 18. Is that less than or equal to 0? So this would be 16 minus 36 plus 18. Okay, 16 minus 36 is negative 20 plus 18. Negative 2 is less than or equal to 0, so that would be a true statement. So yes, everything in the center works. Now I'm going to check my last tester value, and my last tester value is 7 is what I selected, but you can select whatever you want. Again, I advise you to keep the numbers as small as possible just to make it easier, although you could just stick it all in your calculator. Okay, so right now I want to know if this is less than or equal to 0. So this would be 49 minus 63 plus 18. And you can get your calculator to assist with that. So 49 minus 63 plus 18 is 4. And 4 is not less than or equal to 0. So this is a false statement, and therefore no, nothing in this interval works. So the only values that work are the numbers between 3 and 6. Now you are actually going to include those numbers because of this equal sign. So anything between, including the endpoints. So final solutions. Would be anything from 3 to 6 inclusive of those endpoints. Okay, moving to the next example. Now we begin factoring again. This just happens to be a quadratic trinomial that is a little harder to factor just because it has a leading coefficient of 5. Again, you could use guess and check if you'd like, or You can use splitting up the middle term, whichever method you prefer. And, you know, if you don't like the method that's being used in the lecture video, then you can always ask me for additional methods to use to see if one hits home a little bit more quickly with you. So these numbers are, again, not that big, so I'm just going to go ahead and break them up because they don't have that many multiples. If they had a bunch of different ways that you could break this down as well as this, then maybe I would suggest splitting the middle term, but that's not really the case. For instance, this can be broken up only one way, 5x times x. The 6, yes, you do have a couple of options. You could either go 6 times 1, or you could go 3 times 2. Now, since we're trying to get 29 in the middle, I know that we can get pretty close to that if I use this combo right here, and I arrange the 6 back here and the 1 right here. Because I can get 30 out of this, and then by subtracting 1, bring myself back down to 29. So the bigger product here, I want my number in the middle to be positive. So the bigger product is going to be this 30x. I'm only going to get a 1x right here. So the bigger product, I want that to be positive, and I'll let this product be negative. So that'll get me up to 30 and then bring me back down by 1 to give me 29. Then, of course, that number times this is how you get that last term, so we're good. And we have factored 5x squared plus 29x minus 6. Okay, so we're wanting to know when this is greater than 0. Right now you need the boundary points, and sometimes you can just look at it and tell what the number is that's going to create a 0 here. And some of you may be able to tell what number makes this 0, but others may need to make a little equation out of it. So the number that's going to make this 0 and is therefore a boundary point, or what we call a cut point on the number line, is x equal to negative 6. I didn't leave room to put my negative. And then what's going to make this 0? Well, you might be able to tell that it's 1/5, and maybe you can't. If you can't tell that it's 1/5, then just make a little baby equation out of it and solve it. You would be bringing this over here, leaving you with just a 5x on the left-hand side. Then you'd be dividing by 5. And then eventually, if you did have to go through all the steps of solving, you would find out that 1/5 is what makes this 0. 5 times 1/5 is 1. 1 take away 1, 0. So we're going to cut up our number line using the number 1/5 and using the number negative 6. So negative 6 occurs before 1/5. I'll just put those two numbers on my number line and go about picking my test points. I'm going to use negative 7 in this leftmost region. Passing between this negative and this positive, I'm going to use 0. And over here, I'm going to use the number 1. Okay, so I have my 3 test points that I have chosen. Okay, these are my test points. What you saw me doing here were my cut points. I'll just write cut points since that's a little bit easier, quicker to write than boundary points. And I'm going to start testing now. So remember, you're testing in the original polynomial. I'm going to test the negative 7 first, right in here. Probably going to need your calculator. Okay, so we're questioning, does this come out greater than 0? And you can put it all in your, you know, if the numbers are a little bit bigger, like in this problem, you can put it all in your calculator. So you can go 5, that's going to be 49 times 49, or put the powers in there if you want to. Plus 29 times negative 7 minus 6. So I ended up with a 36, and of course that is greater than 0. So we got a true statement here. So that's going to be yes. that everything in this interval works, because testing the -7 tells us that that's true. Moving on to test this 0, it's going to be 5 times 0 squared plus 29 times 0, and this 0 is really easy to test because that would be gone, that term, it would be 0, therefore it's gone. This term would be 0. All you'd have left is -6. Is that greater than 0? Nope, that's a false statement, and therefore nothing in this interval works. So that's a no in there. And then moving to the right and testing the number 1. So we're going to have 5 times 1 squared plus 29 times 1 minus 6. Is that greater than 0? So this will be 5 plus 29 minus 6. Okay, so it's basically 5 plus 23 is 28. That's greater than 0. Yes, that is a true statement. So yes, everything in this interval actually works. So we're going to talk about all the numbers in this interval, which are 1/5 all the way out to positive infinity. We're also going to talk about the numbers in this interval, which are -infinity all the way up to -6. Will we include these endpoints with a bracket, or should we use a parenthesis? That has to do with this symbol right here. Notice that it has no equal sign, and therefore we will not be using a bracket. We're going to use parentheses around those endpoints. Okay, so final solution is going to be, remember, read these answers, state the answers, moving across this number line from left to right. So all the numbers out here are called -infinity up to, but not including, -6. So -infinity all the way up to -6, but not including that endpoint. Or you can also find other solutions on the right tail end of this number line. And that would be all values from 1/5 to positive infinity, since this number line does go on indefinitely. So everything from 1/5 to positive infinity. And that would be your final solution. Okay, moving on to the next example. And in the next example, the factoring method is taking out the greatest common factor. This is not a trinomial as in the last two examples that I did. Okay, notice that there were 3 terms there as well as there, and I used guess and check to factor both of those. Okay, so this only has 2 terms and they have a common term. So x is what we're going to take out. That leaves you with x minus 4. We're looking for situations where it's greater than 0, but we need the cut points first. So you ask yourself, what would make each of these factors 0, which is sometimes very easy to tell just by observation. In this case, it is. So what would make that factor right there 0? Just plugging in a 0. So x equal to 0 is one of your boundary or cut points. And what would make this factor 0? X equal to 4. Okay, so these are your cut points. We are going to cut up your number line into different intervals. So we're going to have a 0 on our number line. We're going to have a 4. Then those cut points separate your number line into 3 intervals. I'm going to choose -1 to test out this leftmost region. I'm going to use the number 1 to test the middle region, and I'm going to use the number 5 to test the rightmost region. Okay, beginning using those test points. Okay, I'm going to use it in the original inequality. I have x squared minus 4 times x. Looking to see which of those test points gives me a value greater than 0. First I'm testing -1. This will be 1 plus 4, because in the middle it's negative 4 times negative 1. Is that greater than 0? Most definitely. So this number represents an interval of numbers that all work. Okay, so we now know that the leftmost interval of numbers are all solutions. Checking out the value 1, which I've selected as a test point in the middle, and plugging it in the original inequality. So 1 squared minus 4 times 1, is that greater than 0? Well, we get negative 3 this time, and that is false. Negatives are not greater than 0. So that means nothing in here works. Okay, moving to the rightmost region and using the number I've selected as a test point in that region, plugging it into the original inequality. So it's going to be 5 squared minus 4 times 5, and trying to see if the value I get is greater than 0. This will be 25. This will be 20. We end up getting 5. That is most definitely greater than 0. And so everything in this rightmost region does work. So now as we state our answers, just as we've done in all the rest of the problems, we're going to state the solutions moving left to right, picking up the smallest values first and proceeding to the greater values. So final solution. Okay, it's everything from out here, which is called negative infinity, up to and including, and let's see, are we including? No, we're not including the end point. Well, we're going to include it, but with a parenthesis. So that actual end point of 0 doesn't work. Okay, so we're going from negative infinity all the way to 0. But not actually saying that that 0 works, which is why we have a parenthesis on it. And we know to put that because there's no equal sign right here. Okay, so that's one area of solutions. Or you can also find plenty of solutions in this other area. Anything from 4 to positive infinity. All those values would actually work in the inequality as a solution. So anything from 4 to positive infinity. Okay, and before I go on to the next page, I'm going to make sure I got everything right. Negative infinity to 0, 4 to infinity. On this previous problem, it was everything from negative infinity to negative 6. We have that. Everything from 1/5 to infinity. In this, the first problem at the top of the page, it was just everything between 3 and 6. And there were brackets around that because each of those endpoints, each of those numbers actually work when you plug it in, as indicated by this little equal sign. Okay, moving on to the last page, where we have a couple of more different kinds of factoring. I put this one in here just because I want you to know that you need to put this in standard form first. In other words, bring everything to one side. And you specifically want to move things in a way that is going to get your x squared to be positive. And so we're going to bring this over here as well as the 15. And you know that each of these terms is going to switch signs as we move them from the right side to the left side. So we're going to have positive 2x squared, and we're going to have a positive 7x that was already there, and we're going to have a negative 15. This symbol will be just as it was, with a 0 now on the right-hand side. Okay, this particular method for factoring would be guess and check, but the harder version of it, just because there's something bigger than a 1 out here. So slightly more challenging. And while you're factoring it, you can just use a little equal sign, or you can use the same symbol. It really doesn't matter. You're just looking for the cut points right now. You're going to have to get it factored. So, in factoring this, when factoring a trinomial, you are breaking up this front term into two factors, and there's only one way to break up a 2x squared. In one position, you're going to have to write 2x, and in the other one, you're going to have to write x, because you're always forced to break up the x squared. That's why you have to give 1x here and 1x here. In filling up the back position, it'll be the factors of 15, which can either be 15 times 1 or 5 times 3. That number is pretty small in the middle, so I would keep it small. I would go with the smaller pair. Instead of 15 times 1, I'm going to try the 5 and the 3. If I do put the 5 here, that's going to give me 10x. I could put the 3 here. Now, once I get up to 10x, I'm already too big for that middle term, so I want to bring it down by making this a negative. So it'll be positive 10x minus 3x will bring you back down to 7, and then of course that negative 3 times 5 gives you the negative 15. So this is factored properly. The cut points, if you don't see what they are, you can just make a little equation out of each factor. So here's this factor, a little equation made out of it. Bring the 3 over here, and it's 2x equal to 3. Then divide both sides by 2, and you get x is equal to 3/2. That's going to be one of your cut points. This one is just easy to tell what it is just by looking at it. What would, when you find this solution, you're finding the number that zeroes this out. If you put that right in there, 2 times 3/2 would be 3. 3 times 3 take away 3 would be 0. But this one you can just eyeball it and tell that negative 5 would cause a 0 right there. So x equal to negative 5 is your other cut point. So we have this and this as our cut points. We'll put those on our number line. And then what we're going to do is choose some test points. I'm going to use negative 6 in this region. I'm going to use 0 in the middle region, and I'm going to use, this is 1.5, I'm going to use 2 in the rightmost region. So these are my test points. Okay, then as you begin to test the points, you're going to test them in the original inequality, which here I go, testing negative 6. So it's 7 times negative 6 is greater than or equal to 15 minus 2x squared. This will be negative 42. This will be 15. This will be 36. Any number squared is positive, but then times negative 2 is going to make it negative 72. So 15 minus 72 is negative 57. So negative 42, is that greater than or equal to negative 57? Yes. Because if you're on a number line, negative 57 is further to the left, which makes it smaller, and that's what this inequality symbol says, that negative 57 is the smaller value, and that 42 is negative 42 is the greater value, and that is true. Okay, so everything in this rightmost region is actually a solution for the problem. Okay, then testing 0, that's in the middle. It is 7 times 0 in my original inequality. And on the right-hand side, it's 15 minus 2 times 0 squared. So on the right-hand side, it would be just 15. 0 times 2 is just 0. So we're comparing 0 to 15. Is that greater than that? That's a false statement. And therefore, no, nothing in this area works. Okay, plugging in my last selection of a test value, which is 2, into the original inequality. So it's 7 times 2 is greater than or equal to 15 minus 2x squared. I am trying a 2 right now. So it's 14 over here. Is that greater than what I'm going to get here? So here I have 15. This is 4 times 2 is 8. Okay, so 15 minus 8 is 7. While over here I have a 14, and that's definitely true. So yes, everything on the rightmost, in the rightmost region actually works. Picking up those solutions and then reporting the final answer in interval notation. So here's the final solution set. Final solutions in interval notation. So it's everything from out here, negative infinity to, now don't accidentally use your test points in your solution set. You're using the numbers on the number line. You're using these boundary numbers, -5 and 3/2, which we got at the beginning of the problem. So it's everything on the number line from negative infinity up to and including -5. Okay, because of this equal sign that's in the problem, I'm going to actually use that endpoint, encasing it in a bracket. Then the other numbers that also work is anything from 3/2 to positive infinity. Okay, and that is your final solution set. Okay, then moving on to a problem that's going to force us to use factor by grouping. So let's see if that works. We have 4 terms, which is the primary time that we're using factoring by grouping. If you group the first 2 terms together, what they have in common is x squared, and then what goes in this parenthesis is x minus 3. Then if you go to the back 2 terms, you have, let's see, nothing in common, but if you want the expression that you are going to have here in parentheses, if you want it to match this, you're going to have to take out a -1. That'll leave you with the same expression here as you have here, which you need if you're going to go on for to do the third step in the factor by grouping process. So -1 times x is that negative x you see there, and then -1 times -3. -1 times -3 is that positive 3 that you see there. And in factoring it like that, you can see that you can now go on, because now you're going to treat this as one term, this as the other term, both of these terms having the x minus 3 in common. And then what goes in this second parenthesis are the items out front, the first and the second GCF that you pulled out. And so here we are, we have pulled out a common factor 3 times. We pulled out an x squared from the front 2 terms, leaving us with x minus 3. We pulled out a -1 from the second 2 terms, leaving us with an x minus 3. And then finally, as our third GCF, we pulled out x minus 3 from these 2 terms, leaving us with x squared minus 1. And it turns out that we can still factor. You can still factor because you have difference of squares here, which can be broken down further. Everything needs to be first degree if you're going to put it on the number line. If you're going to get cut points from it to put on the number line. So difference of squares, if you remember factors like this, you take the square root of that first term, which is x, and put it in the front position of each parenthesis. You take the square root of the back term and put it in the back of each parenthesis and alternate the signs. So now for the first time, we have an inequality that's been factored, and we have 3 factors this time, and therefore our cut points are going to be, these are easy enough to just look inside each of the parentheses to figure out what would zero this out, what would zero this out, what would zero this out. So here it would be x equal to 3. If you were to plug that right in there, it would zero it out. If you were to plug in x equal to -1, that would zero that out. And if you were to plug in a positive 1 there, it would zero out the third factor. So these are going to be our cut points on our number line, and it's going to create 4 different intervals. Okay, so we have -1, +1, and we have +3. So if you have 3 cut points, you're going to have 4 intervals. You have the interval to the left, interval in here, third interval, fourth interval. And we're going to test a number in each interval. I'm going to test -2. In between -1 and +1, 0 occurs. I'm going to test 0 in there. In between 1 and 3, 2 occurs. I'm going to test 2. And out here to the right of 3, 4 occurs. So I have a lot of testing to do on my test points. Okay, so I'll try to squeeze all this in. Okay, here I go, testing -2. Okay, so it's -2 cubed, then it's -3, -2 squared, minus -2 plus 3. Is that less than or equal to 0? Now I'm going to put this in the calculator just to reserve room. So this is going to be -8. It's going to be 4 times -3, which is -12. Let me just put this here so I can show you what I'm doing. So I put in this and got a -8. You can put the whole thing in the calculator with the powers and the parentheses and everything. I'm doing part of it in my head. Like I'm doing 4 times -3 is -12. And then in here in the middle it's +4. And then right there it's +3. So I get -13. Is that less than 0? Yes. This is a true statement. Okay, so we're going to put yes right here. Then we're going to go on to this next number, which is a 0. And when you go and put the 0 in, it's 0 cubed minus 3 times 0 minus 0 plus 3. Is that less than 0? So this term would be gone, this term would be gone, this term would be gone. All you'd have left is 3. Is 3 less than 0? Nope, that is false. So no, nothing in there works. Moving on to the next tester value, which is 2. So it's going to be 2 cubed minus 3 times 2 squared minus 2 plus 3. Is that less than 0? Okay, so here's the calculations. 2 cubed is 8. This is going to be 4 times -3, which is -12. Then it's going to be minus 2 plus 3, which is -3. -3 is less than 0, so here we go with another true statement. And therefore, everything in this area actually works. So we have another yes interval that we'll talk about in our solution. The last tester point that we're going to use is the 4. So it's going to be 4 cubed minus 3 times 4 squared minus 4 plus 3. Is that less than 0? Okay, so putting these numbers in the calculator, 4 cubed is 64. Okay, so it's 64. And then this would be 16 times 3 minus 4 plus 3. Minus 4 plus 3, that gives you 15. Is 15 less than 0? False. That is not true. Okay, so now let's talk about in our final solutions. the numbers that work. So everything in this interval all the way on the left is negative infinity all the way up to, don't forget you're using the numbers on the actual number line, not the tester points when you give your final solution. So everything from negative infinity to -1. Should we actually include this endpoint called -1? No, we should not, because there's no equal sign underneath this absolute value. Underneath this, inequality symbol. So this is going to be negative infinity all the way up to -1, but not including -1. So there were some solutions there. And then there's also solutions between 1 and 3. Or you can find answers between 1 and 3. Okay, so when you're trying to say you have solutions between two numbers, you'll see no infinity symbol in there. You'll just mention the two numbers that you're squeezed between. But if you're going off to the left, you'll mention negative infinity. If you're mentioning this interval all the way to the right, then you'll have a number, comma, positive infinity. But you've seen several examples of that here. Okay, now we get to one like you're going to see at the end of your homework in my math lab, and it relates to the very first picture that I gave you in this section, where you could see what the boundary points are. So you have boundary points here, and they're telling you what that x value is, just in case you couldn't make out what it was, which you were likely not to be able to do. So they told you it's -2/5. This one is very clear. You can see that that is -1, -2, -3, -4. So right there is -4. And then you can see 1, 2, that this one is 3. Okay, so if you use a polynomial graph, give the solution in interval notation. So you are looking for, even if you were to bring this all on one side, not that you need to, if you were going to solve this yourself, then you would need to, because you'd have to factor the whole thing. But just so you can understand that this is a greater than situation, even if you were to bring all these terms over here, bring the 58 over here, it would become -58, bring the 24 over to the left as well, and it would be -24, and you're looking for, a greater than situation. So if you're looking for a greater than situation, you are looking for, and again, this relates to the very first, the beginning of this lecture in section 3.6, where I was talking about what constitutes solutions for greater than and what portion of the graph constitutes solutions for the less than case. We're looking for the greater than case, so that would be x values that lie on the portion of the graph that is above the x-axis. That's what you're looking for whenever you have a greater than case. Portions of the graph that are above the x-axis. So that would be that portion right in there. And you want to specifically talk about the x values that go with that portion. This portion of the graph is also above the x-axis, so you want to talk about the x-axis associated with that. So I'll write out here what I just said verbally. What are the x values associated with the portions of the graph that are above the x-axis. Okay, again, above because you're doing the greater than case. Okay, so this x value right here we already know is -4. And then all these x values, because they are moving to the right of -4, my pencil is moving to the right of -4, they're all greater than. So it's like, negative 4 point something, negative, let's see, -3, -2, until you get all the way to -2/5. So these are all the values. All the x values associated with this above portion are x values that are between -4 and -2/5, because that's the x value that goes with that boundary point right there. So everything from -4, and I'm using brackets because the original inequality has a little equal sign in it. Everything from -4 to the x value -2/5 is a solution, or you can also find solutions for this other portion that is above the x-axis. And that would be an x value associated with 3. And since this leg flares out, all the x values on this above portion are all greater than 3. So it would be everything from 3 to infinity. Okay, and that concludes the lecture for section 3.6.